From our discussion on search algorithms, we found that it's much more efficient to write a binary search algorithm, but a binary search requires the list to be in sorted order. So that begs the question, how do we get a list in sorted order? Well, now we'll talk about that class of algorithms, sorting algorithms. So we'll start off talking about two sorting algorithms, insertion sort and selection sort. So insertion sort works by moving through the list from left to right and building up a list of sorted elements from the larger list of unsorted elements. So everything on the left side of the array is going to be considered sorted so far. So we describe that in terms of an invariant, which is some property of our algorithm that is true at every step of our algorithm. So the main invariant in insertion sort is that taking some element I, the current element we're trying to place in our sorted list, from every element starting at index 0 up to, but not including I, so everything to the left of index I is sorted at the ith iteration. So that's element 0, 1, so on up until index I minus 1. And we'll say that at the ith step of the algorithm, everything from index 0 to index I minus 1 is sorted. So that's our left portion of the array. Then we have index I, which is at the ith step, we are trying to insert that element into our sorted list. And then everything above I, so I plus 1 up until n, those numbers are still unsorted, and we haven't looked at them yet. So we're building up this sorted list going from left to right, and once we reach the end of the array, the entire list should then be in sorted order from index I all the way up to index n. So the way insertion sort looks in code is something like this. We're going to have an outer loop that goes from I equals 1 up until n minus 1. That defines our steps of insertion sort. So according to our invariant, the ith step occurs when I is equal to whatever that step is. Then within each step, what we want to do is we want to take the element at index I and we want to shift it over through a series of exchanges until it is in the correct position in the sorted list. So we'll start at index I and work backwards, decrementing j until j hits 0, or until our element has been moved to the correct position. So we'll start where j is equal to I, and we'll check whether the element at index j minus 1 is greater than j. So if the element that's directly to the left of our current element is greater, then that means they can be swapped to get a better sorting. So we'll perform an exchange, and we'll swap the element at index j minus 1 right here with index j. Then we'll keep doing this process, because let's say this element, our original element I, was negative, it was really, really small, and we have to exchange it all the way to the front. So this loop will continue doing a series of exchanges until this element has been exchanged all the way to the front. That's our terminating condition, as long as j is greater than or 0, or until this is no longer the case, that the element to the left is smaller. So at that point, that element is now in the correct position in our sorted list, and we'll break out of our inner loop and back out to this loop. We'll increment I, and we'll perform another step of insertion sort. So now, we'll have you try tracing through an insertion sort, given this array, B, D, A, E, C. And in particular, we want you to show, for every step of the algorithm, what is the sorted portion of the array, what is the current value of I, what are the values of j that will get looked at, what are the comparisons that are being made, what exchanges are made, and for each of those exchanges, what the array looks like. So for example, at the very start, I is going to be equal to 1, so I is 1 here. The sorted portion of the array is just B. So we say that so far, the list containing B is in sorted order. Great, that doesn't tell us much. And then we're going to try exchanging D into the correct position. So we'll first compare D to the element to the left, B, and we'll say, well, is B greater than D? No, it's not. So we make no exchanges. We increment I, and now our sorted list contains B and D. And this is what the state of the array looks like at the end of our first step. So try tracing out the rest of the steps of insertion sort until the array is fully in sorted order. All right, let's start tracing the rest of the algorithm. So at the next step, I will be equal to 2, and we'll make the following comparisons. We'll check whether the element at index 1, D, is greater than A. That is true, so we'll swap them and get B, A, D. Then we'll compare A with B and see that B is again smaller or larger than A, so we make another swap, A to B. Now A is at the front of the list, we hit our terminating condition, J is equal to 0, and we stop. So now our list is A, B, D, E, C, and the sorted portion is A, B, D. In the next step, I is 3, and we'll check whether E is less than D. It's not, so we break at this point, and we make no exchanges. Now our sorted list contains A, B, D, and E, and I is 4. So we'll compare C with E. C is smaller than E, so we need to swap them. Then we'll compare C and D. C is smaller again, so we swap them. Then we compare C to B. C is greater than B, so we break out and we stop. So in total, the number of comparisons we made was 1, 2, 3, 4, 5, 6, 7. And we made 1, 2, 3, 4 exchanges. And now our array is in sorted order. Okay, now we'll talk about the next sorting algorithm, selection sort. Selection sort is actually similar to insertion sort in its invariant. They are exactly the same. In selection sort, we are also building up a sorted list going from left to right, where there is a current left portion of the array that's sorted and a right portion of the array that is unsorted. However, in selection sort, instead of taking each element and trying to exchange it into place, selection sort works from the smallest element to the largest element and takes the next smallest element and puts it into position. So at the start of selection sort, it looks through the entire array and tries to find the minimum element of the entire array. Once it finds the minimum, it moves it to the first position of the array, the 0th index. Then it looks for the second smallest element, which is equivalent to the smallest element in the right portion of the array that is everything but the first element. Once it finds the minimum of that, it moves it to the front and continues looking for the third smallest element. And it does this process until the entire array has been sorted. So in code, that looks like this. There are n steps to the algorithm, and at each step, we run this loop, which looks for the minimum element in the unsorted portion of the array. Then we swap that element to the front, and we increment I, and continue this process until the array has been sorted. Now we'll have you try tracing through an example of selection sort on this array, B, D, A, E, C. So try filling out the following table by showing which portion of the array has been sorted so far, what is the step value I, what are the values of J, what are the comparisons that are made at that step, what are the exchanges that are made, and what the array looks like at the end of this step. So try tracing through the algorithm. Okay, let's walk through this one. So at the start of the algorithm, our I is going to be 0. And we're looking for the minimum element of the entire array. So j is going to move through 1 up to 4, and we'll make 4 comparisons. So we're going to first compare the element at index 1, whether it's less than b. D is not less than b, so our min's still 0. Then we check, is a less than b? It is, so we update our minimum to be 2. Then we check, is e less than a? Nope. Is c less than a? Nope. And now we're at the end of the list. So a was our minimum element at index 2, and we'll exchange it into the 0th position. So a and b have been swapped, and now a is at the front. So now our sorted portion of the array contains just a, and I moves on to 1. Then we're going to look for the minimum in the rest of the array by first comparing b here to d. B is smaller, so our minimum is going to be 2. Then we'll check e and compare it to b. B is smaller. Then c compared to b. B is again smaller. So we found our minimum. It's at index 2. And we're going to swap it into index 1, our current value of I. So now our array looks like A, B, D, E, C. And A and B are the correctly sorted portion. Now I is equal to 2, which is D. And we're going to compare E and C to it. Well, E is greater than D, but C is less than D. So at this exchange, our minimum index will be updated to 4. And now that we're at the end of the array, we'll exchange 2 and 4 to swap C and D. So now our array looks like A, B, C, E, D. And the sorted portion of the array is A, B, and C. And notice that D got swapped to the end of the array. Now we have to sort the last 2 elements. So we have to figure out what goes at position 3. That's our current value I. So we check, is D less than E? It is, so our min is 4. And then we exchange them. So our array becomes A, B, C, D, and then E. And note that our sorted portion is A, B, C, and D. So for E, our algorithm will be at step I equals 4. J will get set equal to 5, and this loop won't even run. So we're not going to do any comparisons or make any exchanges, and we end up with a sorted array. So in total, that took us 10 comparisons, and we made 4 exchanges. Let's wrap up selection and insertion sort with a Q&A. First, in the worst case, which one performs more comparisons, insertion sort or selection sort? Think about this one. So what is the worst case for each of these algorithms? Well, selection sort is simpler to think about because its function does not depend on the sorting of the elements. You're always looking through every element to find the minimum in the unsorted portion of the list, regardless of what their ordering is. So selection sort is easier to see that at the start, it looks through the entire list. Then it looks through the entire list minus 1, then the entire list minus 2, and so on, down to 1 element. That is on the order of n squared. In particular, n squared over 2, but we ignore constants for order of growth analysis. For insertion sort, it does depend on the order of the elements. So what is the worst case? The worst case occurs when you have to compare against every element of the list every time. So shifting an element from the back of the list all the way to the front of the list every time to get it in sorted order. When would that occur? When you always need to move from the back to the front? Well, that would occur if the array were in descending order, because the minimum elements are always going to be at the large end, and they have to be exchanged all the way over to the front end. That, again, is going to be the same number of comparisons as selection sort. So in the worst case, both algorithms perform comparisons on the order of n squared. Now what about exchanges? Which one performs more exchanges, insertion or selection sort? Well, the answer is insertion sort. Insertion sort has to perform roughly n squared exchanges in the worst case, because every time you make a comparison, you're also making an exchange. However, selection sort only performs a linear number of exchanges, because it first compares through the entire array to find the minimum, and then it makes a single exchange for that minimum element. So every element only gets exchanged once, in the worst case. So it seems like selection sort is better because, well, they both have the same order of comparisons, but selection sort has far fewer exchanges. So wouldn't selection sort be better? Why not use it all the time? Well, in fact, insertion sort is often far better than selection sort. The reason for this is that while in the worst case insertion sort is n squared, that often doesn't happen in practice, because often data sets are sorted, at least roughly, in the real world. So it's often the case that insertion sort performs way better than n squared comparisons. In fact, for lists that are almost sorted, insertion sort is closer to a linear performance, only taking n comparisons. So the reason for this is when the array is almost in sorted order, each element doesn't need to shift that far to get to its correct position. In that case, we only do closer to a linear number of exchanges and a linear number of compares. So in practice, insertion sort often works much better than selection sort. So let's say you're trying to sort a very large data set, like millions of rows. You're Facebook and you want to sort every person on Facebook by their last name, for example. So should you use insertion sort or selection sort for this type of data? Well, selection sort is definitely n squared, so we definitely don't want to use selection sort. But what about insertion sort? Would you use insertion sort for such a large data set? Typically the answer is no, because ultimately these are both n squared algorithms in the worst case. As the size of your data set grows, the potential size of the array that you'll have to shift elements over when you're doing insertion sort grows larger and larger. So for example, if your minimum element or a cluster of small elements happens to be at the end of your array, you're still going to have to shift all of them over the entire length of the array. And as your array grows, that gets worse and worse, and it starts to look more like n squared. So when your data set becomes very large, it's not really recommended to use insertion sort at all. It's much better to use an algorithm with a better worst case runtime, such as merge sort. And that's what we're going to talk about next.